Hello, I'm Yasir. Today I will try to apply the fourth order Runge-Kutta method. Fourth order means that gives accuracy of order 4. So I will apply fourth order Runge-Kutta method to solve the problem using the shooting strategy. So I will apply the shooting method for the problem which was studied in this research article. So this is a paper which is published in International Journal of Numerical Nonlinear Mechanics. And so here in this problem, these are the governing equation, the seven, and then uh, using some approach, this problem reached to this ordinary differential equation. So there was actually, it was some assumptions here, and then first the problem seven, the seven is reduced into into the equation nine, and then using uh, again u du by dx is equal to minus dp by dx using this thing, and pfx is equal to that. The problem reached at 12. And then using this, and then it was mentioned that a global similarity solution does not exist because we cannot get rid of x in 16 for any choice of the parameter delta, gamma, and f. However, we can look for local similarity solution. So for local similarity solution, so the equation is 19 with the boundary condition of 22. So I will try to solve equation 19 with boundary condition 22 using the shooting method based on Runge-Kutta of order 4. So I will bring this equation into the whiteboard because this equation should be written in the form of first order differential equation. So I will convert third order equation into the system of the first order differential equation. So this is the equation. So first I assume that f prime is g and f double prime, which is g prime, that equal to h. And then this equation can be expressed in the form m into f prime is g, so it's g square minus 1 minus m plus 1 over 2 f, f double prime is h minus, now I bring the last term on the other side. So I bring this whole thing on this side, on right hand side. So that equals mu of x and h prime. The f triple prime is h prime. So now I bring mu of x on this side. So if I write mu of x on this side, so this equation can be written as m g square minus 1 minus m plus 1 over 2 fh, and this is h prime. So I write h prime on the left. So now I will apply the Runge-Kutta method, Runge-Kutta of order 4. So I will bring the formula and then apply that formula onto the equations. So this is the formula for the Runge-Kutta of order 4. So paste the formula here, then I will apply. So first step is the K1. So it will be K1. H is delta T. H is the step length, and function is evaluated at naught. So I will express it at n. So it will be written as delta P and G after. And then K, so that would be K11, then K12. So the K12 would be delta T, and this it is H, so it would be H of them. And then K13. K13 would be 1 over mu of x. No, first delta T, and then over mu of x, and then this M into Gn square minus 1 minus M plus 1 over 2 Fn Hn bracket close. So this equation is converted into this form. The second equation is converted into this form, and the third equation is converted to that. So no, I will write the second. I will apply the second stage of Runge-Kutta fourth order with these three equations. So for second, it would be a y naught. It will be a yn, and then half of the previous stage. So I will call it as 21. A21 will be delta T, and then this would be a Gn plus half K1. So for G1, that would be a equation. Second equation, the second equation that would be a K12, half K1, and then that's for G, that's for H, and that's for H. That for H, first for F, and second for G. So K21, and then it would be a K22. K22, that would be a Hn plus half K13, bracket close. And then K23 is delta T by mu, and then there would be a M, and then M into Gn square. For Gn, it would be a Gn plus half K12, K12 square minus 1, and then minus M plus 1 divided by 2. So that's a Fn plus half K11, and then Hn plus half K13. No, this was the second stage I applied on the equation. Now I will apply the third stage. So the third stage is written as stage K31. So K31 will be delta T, and it's Gn plus the previous half. The previous one for G is K22. Previous stage for that's K22. And then K32. K32, that would be a delta T, and then Hn plus half, and that would be the K23, and then K33. K33 would be delta T over mu of x, and then M. So it's Gn plus half. So that would be a K22 whole square minus 1 minus M plus 1 divided by 2. So here it would be a Fn plus half. So no, for Fn, the previous stage would be K21, and then it was Hn So here I did not use half, so this would be, so that would be a half, and then K U3. Now I will write the final stage. Plus final stage, which is y naught plus K3 just. I will not write half now. So K41. K41 is equal to delta T and Gn plus, for G that would be the K3, and then K42. K42 is delta T Hn plus K33, and then K43. K43 is delta T mu of x, and then M Gn plus K32 whole square minus 1, and then minus M plus 1 over 2 Fn plus, that would be a K31, then Hn plus, that would be a K33. So that was the fourth stage. Now I write the Yn plus 1. So Yn plus 1 is equal to, no, first I would have F, Fn plus 1 is equal to Fn plus 1 by 6 K11 plus 2 K21 plus 2 K31 plus K41. So first step, first equation for all these stages. So this the first stage, this one, and then this one, and then this one, and then finally. So 1, 2, 3, and also this one. So these four, and they will be added in those with the weights. So, and then G n plus 1 is equal to Gn plus 1 by 6 into K12 plus 2 K22 plus 2 K32 plus K4, second equation of each stage. And then the third one would be Hn plus 1 is Hn plus 1 by 6 K 31. No, it was not 31. First equation was 2, 2, 3. 2, 3. 2, 3 plus K plus 1, 3, and then 2, 3. Plus 2 K 3, 3 plus K 4, 3, and bracket close. Now I have to construct the code in MATLAB. So for doing that, So here, if, that zero is MATLAB solver that solve the equations. And then for differential equation, I will use the Runge-Kutta 4 method. Runge-Kutta 2 is already applied. So now I will try to apply the Runge-Kutta 4. So, so for doing that, so what I will do, I start from the K K11. I start from this K1. So K11 is equal to dt multiplied by Gn. That's K1. Then K12. K12 is dt multiplied by Hn. And then K13. K13, it is dt over mu, and then it's m multiplied by g n square minus 1 minus m plus 1 over 2, and then fn multiplied by hn and brackets, and then k to 1 to dt multiplied by g of n plus 1 by 2 k1 and then k to dt multiplied by h of n plus 1 by 2 k13. And then k23 is equal to dt over mu from m to g of n plus half k12 whole square, this one that will close, and then minus and plus 1 by 2 multiplied by f of n plus 1 by 2 k1 h of n plus 1 by 2 k13. So that was, and now k3 k31 is equal to del t, and so that will be 2 to to 4 to 4 3. And here there is no half, also here 3. There is no 1 by 2 in the last stage. That will- So there is no 2. this would be a key. This one out. So that would be your K3, K3 when you put this K4, computer. So these are the four stages and then the following is five, six, that eight plus two K21 plus three K31 plus K4. That so H is I'll do two, three, two times. So here this is two, three, this is two. So that's one should be a K23, other is K13. K1, K1, K23, K. I made a mistake. Maintain it. Okay, I will try to. Not say that. I know if I run this. I run this. Skip time. So it's a time, but it is. It's free. If I run it. So decrease the domain and then run the code. So it might work in that situation. So I use the latest updated value. For updated value, I can increase the domain now. See what happens. So this is the solution. File and give it on. So yeah. So this is the updated initial condition. Was yes, not updated. So first not working for the launch. Working. Yeah, this is the solution. So that's a solution obtained by Runge-Kutta about the fourth method. I see the code again because I stay there. To check, I can compare the solution with the PvP4, PvP4 solution. So then it can be checked that the this solution is correct and the method is correct. So here I used 1 to 1 3 and then 2 1 2 3 1 3. Then I think it looks but I can compare with the PvP4 system. Then so it will 2 3 2 2 6 then do 3 and then switch here 1 over mu x 1 over mu that then becomes g is u2 square minus 1 minus and plus divided by 2 and then as such as in u1 is the boundary conditions. Boundary condition so boundary condition at left hand point is 0 and then the condition at derivative is 0 and then the boundary condition at right hand point on derivative. Then I will use initial guess. For initial guess, I use the domain from 0 to 4 points. Then here I will use 0, 0, and then Uh, I will use PVP4 3, and here the first function threshold equation, then the boundary conditions, then the initial value, and then E is equal to 0 to 4 and 50 grid points, and then 3 is equal to 8 solution at E, and then the plot E and E derivative. Whereas on basically, oh, filters. So this is the solution obtained by BP4C. What if I run that? I check, I save the file, explore. Same time, the file, it's pushing the pen by the proceed. Now check this. Copy paste this. So yeah, so both should start matching with each other. So it means that this solution is correct for the solution obtained the shooting method based on fourth order Runge-Kutta method. Now I apply. Now I end this video. Okay, love is bye.